We'll now start quantum entanglement. So, just a quite quick recap. We studied two types of protocols: prepare and measure. Now we have entanglement based. So, the security of the protocols which we will study later. First, we'll talk about entanglement. It comes from two factors. One is the proof that the state which I'm using is non-local, and the second one is it will again fall back to the no cloning theorem and uncertainty principle based. You cannot differentiate or conjugate coding, or you cannot differentiate between two non-orthogonal states with certainty. Okay, so this the security principle will be the ones which I had just mentioned now. With that, we'll start with first, understanding the history of quantum entanglement. So, um, Einstein, had asked this question in 1905, saying that can quantum mechanical description of physical reality be considered complete? Now, this part is important to understand the importance of the the non-locality, okay, which forms the basis of Eckert 91 or BBM 92 or device independent or MDIQKD. So why is this particular aspect important? What was the confusion? Where was the uh, you know uh, what was those initial investigations, and why are we convinced and the world is moving forward with so many applications of quantum entanglement? Teleportation is done, dense coding, and even in quantum computing you have an element of quantum entanglement there. So this was the heart of quantum mechanics. And earlier, the EPR paradox and the Schrodinger's cat, they were all confused. It was very difficult for them to accept one particular feature of quantum mechanics, which was non-locality. So whenever I'm talking about an entangled state, when in the earlier session I was talking about superposition, ket 0 plus ket 1 by square root of 2 can also be can be used to represent ket plus diagonal state, right? So that was superposition. And now I'm talking about two particle state. Okay, two particle state. So it's entanglement between two particles, which does not exist, as a single entity, but rather both these particles, they come together to exist as one. Okay, so this is not counterintuitive. It may seem in the beginning, but it is not. It is very simple. It is just that two particle behaving as one, and you will have to look into the maths to understand the concept and to prove whatever notions or whatever ideas we're discussing it here. So the confusion was regarding non-locality, that how can a quantum entity, any entity, for example, if I'm putting a ball in a box, I discussed it last time also. I know the color of the ball, it's green, and I'm putting inside a box. No matter whatever measurement I do, how many times I measure, it will always be that same color of the ball in the side that box. It will not change based on how I am looking at it. Okay, I'm using the word it will not change on how I am looking at it. In other words, how I am measuring it. It doesn't change. Okay, so these were the factors, and then they had proposed one paper. Based on this paper, Bell had started working whether on an inequality to see if there is some local hidden variable aspect associated with it. And then he had come up with an equality saying that if in the classical world, if you are looking at that particular inequality, it has to be less than or equal to 2, less than 2, then it obeys the classical world. uh, it is what we see. This is how it has to be. And quantum mechanics, if there is something, if it uses some local hidden variable theory, if it is not complete, should satisfy that inequality. Okay, so they had Bell has proposed that. Then Closer, he realized that whatever Bell had proposed, it was very difficult to do it experimentally. So he proposed another interpretation of how of that inequality, and that how it can be done experimentally. That is known as CHSH parameter. And then experimentally, it was shown in around 1981 or 82, that the quantum state violates the inequality. Okay, so it's called Bell violation. So Bell violation proves that it is a non-local state. It's a real. So it became a measure of a quantum state, and anything which is based on entanglement is truly quantum in nature, and it is the highest. It is of highest security. So if I'm generating random numbers, I'm not sure whether I have discussed in this session or not, but if I'm doing a random number generator, then it is of highest security. There is no question of any seed, and even if I'm buying it from some other party, then I know it's secure. It's called device independent or source device independent. Those kind of architectures can be made from this quantum entanglement based devices. So in 2022, the scientists got Nobel Prize for that, and there was also quantum teleportation performed, uh, after the Bell inequality was violated, after a few years, I think 10 or 20 years after that, quantum teleportation application was done. What has happened now is, if something was done there for 30 centimeter and with some imperfect instruments, those has been improvised, and today we are doing quantum communication entanglement based QKD, particularly in hundreds of kilometers. Yeah. So, okay. So I will be earlier had promised you to you show about the key rate with respect to distance, right? I think that was for BBM 92, which is coming soon. And you can see the political significance. So this is the entangled state I was talking about. It's a two particle state. Earlier, I was talking about single particle states, weak coherent states, or a single particle state, right? Now I'm talking about two particle state. Now, again, I would like to mention here that I had earlier mentioned about the categories of based on detection, continuous variable, homodyne detectors, or single photon detectors. So even though it is a two particle state, I will still be using a single particle based, discrete variable based detectors, because I'll be actually sending the two particle state to two different spatially located entities. One may be at Pune, other maybe in Jaipur, something like that. So finally, I'll actually measuring a single particle state. So my detectors will not change here. And what does this state mean? So this state means that it is in superposition. Just imagine this state. You can write the state with HH equal to 0 and VV equal to 1. So it's a superposition state, right? So here I'm talking about two particle state. So it is an HH and a VV. I do not know whether the state will be HH or it will be VV on measurement, but I certainly know that if it is H, if I see H, then the other will also be H. Okay. If I see a vertical, then other will also be a vertical state. And that is the correlation which is exploited to generate secure, symmetric encryption decryption keys, or this random wave function collapse I have used to generate quantum random number generator. Okay, so again, just spending a few more seconds here. If I'm keeping the first particle in this galaxy and I'm sending the second particle in a far off in some other galaxy, and I am measuring the state. Okay, so one particle is here and the other particle is there. I'm measuring the state. If I observe upon measurement H, then the other state in the other galaxy has spontaneously, simultaneously collapse to an H. After having measured this H, I do not know whether the second measurement from the ensemble of states is going to be an HH or a VV. It can be H or it can be VV. So here I'm violating realism. And when I'm doing a measurement, correlated measurement, there I'm violating locality. Okay, so there's a lot of violations coming out here. Localism, realism. Okay, here. So, and the other equation here shows that the state, the two particle state, does not behaves as one. They do not have any existence, or there is no entanglement as a single entity. The entanglement property is there when they are actually entangled, or they are. You cannot, in quantum mechanical language, you cannot write them in separable states. Okay, so so this is the beauty of this entanglement. Now, so this is exactly what I had mentioned you, that this is called spooky action at a distance. That is the term non-locality. Um, Even if they are spatially apart, I do not know. So consider two magic boxes. In one magic box, I have kept one entangled photon. In the other magic box, I have kept another entangled photons. Okay. And I send them apart. And when I'm opening one of them, if I'm seeing an edge, the other one there is an edge, collapses to an edge. If I'm looking at getting a V, other becomes a V. So this is how this works. And, I will not like to go, into deep discussions about different physics associated with non-locality, but let us see how we can extract applications out of this aspect. So now to use it, we will actually have to we have to generate an entangled state. So how do we do that? So just in simple language, if you have a bottle, a glass in front of you, and you're shining a red pointer there, you will see a red light coming out, generated on the other side. Okay, the color of the light doesn't change; the wavelength remains the same. But in a nonlinear generation, nonlinear optics or phenomena, if you're sending a particular wavelength of light, then the wavelength changes after having passing through the crystal. It's a nonlinear phenomena, and it is basically we use this. This is based on a condition which we have to reach based on the direction of propagation of light, the optics axis orientation of the crystal, the birefringence property of the crystal, that uh, all those conditions at a particular time, they reach the phase matching condition, respecting the energy and momentum condition. So this is the momentum, and this is the wave vector. So once we are reaching a condition here, which is known as phase matching, I will see generation of two circular rings intersected at 2 points. So I'm going to fetch my entangled photons from these intersection points. Okay. So now if I'm taking the temporal coherence in a classical field, if I'm sending a bunch of photons, through a beam splitter, I will always get coincidences, right? But if I'm sending a single photon through a beam splitter, I cannot get coincidences at the two detectors, right? So there are some tests we do to find out whether the second order temporal coherence, and for non-classical light it comes out to be less than 1. So again a deviation. So there's a lot of deviations which happens in the quantum world. So we have generated this light, we have found the second order correlation function which is coming less than 1, which is sure shot telling me it's a non-classical light. But then whether it is entangled or not, we'll have to do some other characterization tests on that. So this is usually a beta barium borate crystal. We have used type 2. Type 2, the polarization, the photons which are coming out from the crystal, they are correlated with respect to polarization. And if it is a single type 1, then the polarization of the generated ring is perpendicular to the polarization of the pump. Okay. So So here you have the vertical. So I had discussed first HH and VV, but HVVH are the cases is what we have generated in the lab. And it's a wave function of an entangled state, get psi. 1 by square root of 2 shows half the probability of detection of HV and VH states. It is vertically polarized, this ring, and the second lower ring is horizontally polarized. And from the intersection points, I'm getting the signal and the idler photons or daughter photons, okay, which is about double the wavelength. If I'm using 8405 lambda as input, I'm getting 810 lambda as in the output. This is how the schematic. HWP is by the stands for half wave plate, polarization beam splitter, collimators, beamed dumpers, lenses, filters, mirrors. Yeah, okay, so this is how, and the entire setup is placed on a 60 centimeter by 40 centimeter breadboard. So now I should be showing you a demo. So our team has, kind of become very pro in getting that phase matching condition, and so we did a live workshop where we generated the phase matching condition, and then again we disrupted the polarization, and then you can see the rings vanish, which means matching condition is vanishing, and again we bring it back. So you will see the intersection rings both from the top and from the down from the bottom. So this is the classical light right now. Okay, when we do the quantum experiment, we have to switch off the lights to eliminate the ambient noise. This is the MCCD detector for visual confirmation, where we'll show you the rings, and you will see the laser light screen. You see the intersection point. So this is the first intersection point. Now I think they will move the apparatus so that you can see the upper intersection point. Yes, so this is the upper intersection point, or maybe vice versa. I don't remember right now. And now we will be disturbing the phase matching condition, and you will see the rings vanish. Yeah. So now you can see some hands moving here. We are again changing the polarization to reach back the phase matching condition, and we see them back. So such advanced detectors, such advanced equipments are absolutely necessary if you would want to do some quantum experiments in your lab. You can see the intersection point. Yeah. So if the lights are on, means detectors are off. So we can now, okay. Yes. So we'll go to the next slide now. So this is how the module looks like. This is a test bed. So since we have developed this, the entangled source, we have characterized them, and we have done a quantum key distribution, we have done a quantum random number generation. So we thought that why not bring it together, and it will be good to have it in any center of excellence or in any educational institute where students can see the photon generation, the nonlinear process, how it is generated. They can see the instruments used for detecting. So in any engineering college you have multidisciplinary departments, right? And each and every department will have something to contribute to this technology. So we have recently won a Director General Core Research Award from CDAC in building this platform. And here you can see that the test bed is this in entirety. We are now just putting a box on top of it and trying to arrange them in a manner where it is a little more out of the lab kind of a prototype. And this is your state, and here is your detection optical module, and the single photon detectors are housed inside this box beneath the laptop. And you can see the coincidences here. The coincidence peak, and there are some shielders which we have to use around the table. So this is how the entire setup looks like. The crystal is mounted in one of the 6-axis mounts placed here, and these are very specialized mirrors and even the mounts. It costs, each and every thing will be of a very high, it's in a higher range because it is very specific to particular wavelength, and the coating and the filtering. These are the tuning has to be very precise because I'm talking about alignment of a photon around the table. So here the test bed, again, you can see the state generator and the detection module. We have made the GUI based on for the characterization results. So here we have also drawn lines. Okay, so the laser light coming from the mirror, two mirrors, it passes through lens, filter, and then you will see the crystal, then the two mirrors. Because remember I told you that in entanglement based QKD also there has to be an Alice and a Bob spatially apart. So this one light from the laser will go to Alice and the other light will go to Bob. I hope you're following my pointer. So one will go to Alice and the other will go to Bob. And you can see the light coming out at an angle from the crystal, 5 degrees. So it is a non-collinear crystal. Okay. If had it been collinear, then the pump light and the direction of the daughter photons would have been same. Now, again, the blue light will be of some milliwatt, and the red light here is in picowatt. It's 1 in billion, which is giving out this SPDC process. Okay, so now there are some tests which we do. So this is a visibility testing. So we actually, the Alice and Bob will be changing the polarization angles and doing the measurements. So we get an interference pattern for different bases. Okay, and we are getting a very high visibility in the horizontal vertical basis at of about say 98%, and in diagonal anti-diagonal basis at 86%. So we have also validated our results with the scientific from the scientific community. We have, so this is something which I have already shown you live in the demo, and these are the experimental results from the plotted from the uh, readings we have got, and these are quite neat, and we have also benchmark these results with the national and global community, and we are almost at par. And here it's so the tomography where I'm using the measurements to reconstruct the quantum state. And here, of course, we have used a tool where we have fed in our data and we have got the results, which also shows a high fidelity. Then the Bell violation, remember I told you that it has to be less than 2, then it respect of it, it violates that inequality. So the value of S has to be greater than 2 to 2 root 2. Okay, so it has to be less than 2 root 2. It's greater than 2 and less than equal to 2 root 2. So we are getting a value of 2.679, which is very good, which is very closer to the highest bound. So why this kind of a thing is important? Because these they form part of the quantum network test bed, and there are some institutes who are working on quantum internet. So in quantum internet, you are actually adding different prototypes. You are doing quantum teleportation, you are doing quantum you have quantum repeaters, you have QKD, you have different types of QKD, you have entanglement based, you have prepare and measure based, you are working on different QKD topologies. So basically from a user side, you'll have to look into the topology, and you have to try to understand what kind of a QKD fits into that topology or will be meaningful in that, and from there you build the network, and then from terrestrial you connect the network to the aerial part, which are trusted, which are quantum relays. Basically, the we are working on entanglement based communication on a drone platform. So what you are seeing here will be mounted on the drone. Entangled state generator will be mounted on the drone, and we have Alice and Bob, two receivers in the ground station, and we'll be sending light entangled photons from the drone to the ground station, and we'll be doing a QKD between two ground stations. So again, a departure from the prepare and measure, where Alice and Bob are doing QKD. Alice is generating, sending, Bob is receiving, measuring. In entanglement base, there is a third party who is sending the quantum light. There are two receivers, Alice and Bob, who are receiving the quantum light, and the QKD happens between Alice and Bob. So if there is a situation where you cannot have a terrestrial network, you cannot have a ground station, satellite ground station, a difficult terrain perhaps, then I may want to put up two mobile quantum receivers. The two receivers are in some wall-like zone, okay, and they have to be kept some distance apart. I need to generate keys, symmetric communication, for symmetric communication. So I can send a drone. Drone will send the quantum light. The quantum light will be received by these two detectors in the receiver module, and they will be generating the encryption decryption keys. The two receivers will can be housed with some bodies which will be using the keys, and then these two receiver can also travel back to the source. Okay, so these kind of agile network, using drone, of course it gives you reconfigurability, maneuverability. So so we are actually working on application prototypes, and we are using this technology, and we are working on those application prototypes. So for that, first we have to validate whether it is a QK, whether it is a quantum entangled light or not. So for that, both Eckert 91 and BBM 92, they will be using these tests which you are seeing here to validate whether the light is quantum or not. If it is quantum, then they trust, then there's some kind of a security framework it satisfies, okay, and it gives you a reliable cryptographic keys which can be used for encryption decryption. So the first protocol which I'm going to talk about is BBM 92. Bennett Prasad Mermin, 1992. They have developed this protocol. So they are using again a rectilinear basis. I hope by now you can recognize a rectilinear basis state and a diagonal basis state. Okay, yeah. Sure. So a diagonal basis state. So here again, I mean, Alice will be using these two bases. They both will be using randomly random bases to encode the state. You can see here Alice has used diagonal bases to encode, and Bob has used rectilinear bases to encode. So I'm going to drop this key. Okay. In the second example, Alice has used diagonal basis. Bob has used diagonal basis. Therefore, what is binary 0 for Alice is the same binary 0 for Bob. Okay. And now they are getting, so because of the antisymmetry, if Alice gets, because we are doing VH plus HV, so if Alice is getting 1, then the Bob will be getting 0. So they are correlated, and I'm getting the correct result. Okay, remember I told you incorrect measurement will lead to wrong result, and that is the reason I dropped it here. So and this communication happens during sifting. So in quantum, if you remember the stack which had shown yesterday in the session on prepare and measure QKD architecture, right? So this is a quantum data transfer which is happening. okay, where Alice is generating these states and sending it to bomb, quantum data transfer. And the sifting is where they will be talking to each other on the classical line, optical, or it can be an IP network, and they will be discarding the states where they are not the same basis. Here as again, Alice is rectilinear, Bob is diagonal, so they are going to drop it. Similarly, here they both are rectilinear. So what is 1 will correspond to 0. Now this is non-local, because you can put Alice in one galaxy, Bob in the other galaxy. Still, you will be seeing this correlation happening, happening instantaneously. Under a particular, because when you are saying instantaneously, it has to be under a framework. Then they accept it, and this way they are generating symmetric keys. So this inversion, because I know that what it is a VHHV model. So if it is 1, then the Bob will be getting 0. So I will be inverting, and in this manner, I will be getting a symmetric keys at both the ends. Okay, so it is simple, no? I mean, you see, I mean, um, this is absolutely neat and very, it's very simple. Any perturbation, still now there is no perturbation. Okay, there is no eavesdropping I'm discussing right now. It may get a little complicated. So I would suggest that you can try intercept and resend attack using the prepare and measure models, which we had discussed earlier, particularly BB84, B92. Okay, but and for polarization encoded, phase encoded again will become a little complicated. So, and here B92, it's absolutely fantastic on how the different bases they are changing, and whenever it is in sync, they are generating uh, symmetric results. I hope you understand why the inversion is done, right? Had it been HH plus VV, then this inversion would not have been required. Finally, you're getting filtered key security. um, so some testing for errors will be done. So now after they have got the sifted key, they will be separating a part of the key from the sifted key for error correction. I had yesterday had mentioned 25% of the key. Suppose you have got 100 keys, then 25 will be sent from Bob to Alice to verify whether whether how much error is there in the system. It's again very interesting to see how the error is distributed and how this error correction is done. It is not very simple to say. We have to do a lot of study in understanding the error distribution and the causes of errors. Particularly is the imperfections around the implementation, something which is limited by physics. We cannot do anything, but some certain refinements we have to, which we can make, we try to make. Okay, and 25, and then there is a sifting also, no, half sifting factor is half here, so I'm losing bits because of that also. So final key is very less in number, no doubt. So any MDI QKD or entanglement based QKD, though the security level is extremely high, the the keys are, throughput is less. So this is one demo which one of my team member has made, that suppose this light is traveling from laser, it is going to the type 2 crystal. We select the photons from the intersection points. From there, they travel through the polarizers, filters, and from free space, we send it to the fiber. And from fiber, they are collected. Again, the conversion. So I'll just repeat this again. The laser is going to come out. Let me play this again. So you can see the light again coming from one mirror to the other mirror. So all this will happen inside the drone. And when the light comes from the nonlinear crystal, it is separated into two. Again, it is happening in drone itself. We are filtering it and then sending it down. From the receiver, there will be some collection optics. And from C1 and C2 part, they will be collecting the light through this optics, through the fibers. And then there are detectors You can see detector, TDC, synchronizer, FPGA unit, and then GPU. All these systems will happen inside this box, and finally Alice and Bob will be sharing some secure key for any cryptographic activity. You can see here um, acha, 5 degree because it's a non-collinear. Had it been collinear, the light would have traveled straight. And there are other methods also to separate the light. We are also attempting collinear based entanglement distribution. So I hope this setup brings clarity. You have seen the model, the entanglement setup in the first slide, no? When we started discussing about the entanglement, the setup remains the same, where we had shown the entanglement distributor setup one, and then there was a separate board for Bob. So those remains the same. So I'm able to do 2 to 3 different experiments on the same platform. Now, what is interesting is how I am generating the final key rate. Okay, so earlier I had mentioned about the errors. So in a practical system, you have um, error versus the total count. That gives that gives you the practical picture of the system error. Okay, but when you're doing a simulation, then you're trying to find out what can be the possible errors which can happen. Now that can happen when you're getting some false coincidences. So basically the coincidence events is generating your keys, your symmetric keys. Okay, so there can be some false coincidences. For example, you're not a coincident, you're not getting entangled photon, you have one of the detector clicking, okay, because of some noise in the system or ambient light, and at the same time the other detector is also clicking because maybe there's an entangled photon, but that you're not getting a pair, you're just getting one of that photon. So but you will get a coincidence. So this is an example of a false coincidence. Another can be both the detector, one because of dark count and the other because of coincidence or because of ambient can click. Both can click because of ambient, both can click because of dark counts. So those are the false cases. Okay, so those cases, theoretically, while doing the calculation or estimation, finding out the estimation, we consider these aspects also. Then b b means that there's a system threshold error rate, and even if you are getting true coincidences, but because of the error, system imperfections, you are bound to get this much of an error. Hmm? So what I can do is I cannot, I may would want to reduce my false coincidences as much as possible to improvise or to decrease my errors and to maximize my coincidences. So these are the techniques which I will be employing uh, to um, to calculate or to improvise on the performance of the system. And if you remember yesterday also I spoke about the final key rate. Okay, so here I just spoke to you about the clicks, which is right click and the signal click and the dark count click. And the signal click is basically because of the mean photon number and the transmission efficiency. The transmission efficiency is limited by the detector efficiency and also by the loss of transmission between Alice and Bob, and the loss of transmission at the Bob's side. Okay, so even if you are sending some very faint signal, you are anyway the signal is getting absorbed during transmission, so it's going to decrease. It's become to get more faint. Maybe I'm not putting it in the proper words, but it's very difficult, and that is one of the reasons I you cannot extend the distance of QKD beyond a certain limit, and you do not have a quantum repeater also. Classically also you are bounded by 80 kilometer, and then you have a classical repeaters, and again you do a retransmission. But in quantum you do not have a quantum repeater. If you want a quantum repeater, you need entangled states. Okay, so quantum repeater is not possible for prepare and measure kind of a protocol also. So this is the loss which happens at the detector module. And then this is the information loss which is happening, because whenever you have an error, you are always talking to the Alice when you are sending the error bits to them, and you're communicating the parity information of a sample. Okay, and that is also giving out a lot of information regarding the keys. So we kind of try to quantify the leakages happening because of the E here stands for the cause of different causes of possible errors. Okay, so this is how the amplification factor or the shrinking factor comes into play. Yesterday I discussed about the Shannon's entropy. So then you have the transmission, the raw light, the rate. Half stands for the shifting factor. Then P stands for the coincidence, because here for an entanglement based QKD, we will be only using the coincidence counts as which will contribute to the key rate. Okay, and here you can see, so you can always do experiments. You can actually simulate this in Qiskit. BBM92 or Eckert protocol can be simulated. BB84 can be simulated in Qiskit. So that is one platform I had shared with you. But in Qiskit, these things are possible. It is difficult to do. It is difficult to do entanglement, no, a nonlinear process generation in Qiskit. It is also difficult to do uh, prepare and measure phase encoded kind of a protocol in Qiskit, but then people have used OptiSystem, you know. So those frameworks are possible. You can come up with some new QKD protocols and you can try to implement them, validate them using these platforms. And I was talking to you about the BB84 Poisson distribution. You see the because in Poisson you have finite probability. This is very important. Okay, what I'm telling right now. You have finite probability of multiphotons, so my leakage is higher, and because of the leakages, okay, the shrinking factor is so high that I cannot scale it up more than maybe 25 to 30 kilometer of fiber length. Okay, I cannot scale it higher, even though my light the the light strength is more than a single photon. BB84 ideal single photon is this one. Even though my light intensity is more than the light intensity here, but still my distance is lesser because my leakage, because of various factors, because of different attack scenarios, is way higher, and therefore I cannot go more than a particular limit. But if I'm having a true single photon source, then I can go way higher, more than 100 kilometer. And BBM92 is an entanglement based, it's a parametric down conversion based. Okay, so if it is an ideal scenario, then you will be going more than, or say around more than 180 kilometer. Okay, again, it depends upon the detector efficiency, dark count, it depends upon the various parameters. Okay, so this is something which can be generated, and you can do a lot of performance evaluations of different QKD protocols. Now we'll go to the Eckert 91 QKD protocol. So I think I'm left with just two to three slides now. Great. So Eckert 91 was proposed by Arthur Eckert in 1991. So again, before moving here, please remember the security framework for this was no cloning theorem and conjugate coding. Okay, and though I'm using entangled state here, I just ensure that I'm using an entangled state, but I'm not verifying my entanglement. My security is based on no cloning theorem and conjugate coding, non-orthogonal states. Very important. Okay, so now I'm going to Eckert 91. Here, it's a landmark entanglement-based QKD scheme that uses violation of Bell's inequality to ensure security. It's a very important protocol. Okay. You may ask me questions perhaps later that, why are you not using Eckert 91? But what I would say that if I propose the platform in your lab or somewhere, if somebody takes it in a center of excellence, I would go with Eckert 91 than a BB92 because of the reasons which will come in the next slide. And this is an absolutely fantastic package for education. You will learn about entanglement generation, entanglement manipulation. You can do different applications and QKD at the same time. So, what is it about? I'm generating an entangled pair generation, just like the BBM92. A source prepares a large number of photon pairs in a maximally entangled state. What does this mean? Maximally entangled means 1 by square root of 2. Half, okay? If otherwise it will be biased. If it is not half, you will not get a max. So it's maximally entangled when I'm saying 1 by square root of 2. So then we have one photon from each pair. I'm sending it to Alice, and the other I'm sending it to Bob through presumably insecure quantum channels. Insecure quantum channels, I told you earlier that I'm using the quantum attacker can attack the quantum channel. Okay, so I'll consider it to be insecure, and I will do all kind of security measurements, evaluations around the quantumness of the channel, about the strength of the channel and the quantumness of the signal which is going through it. I'm not really interested in the classical channel. It's a classical problem. So here I'm addressing only the quantum part with the whatever quantum adversary will do. Now, if these photons remain undisturbed, Alice and Bob share an entangled state upon arrival. Okay, same as the BBM92 till this part. Then random measurements. Alice and Bob each have a set of measurement bases to choose. Just like, but what is the difference? Here it is. Alice chooses between 0, 45, and 93 basis states, and Bob between 135, 45, and 90. Okay, three basis states. So please pardon me. This should come with a degree, but I was actually making the slides a few minutes back, so I wanted to put degrees, but it didn't happen. So please consider them as 0 degree, 45 degree, 90 degree, 135 degree, 45 degree, and 90 degree. So Alice and Bob independently, of course, one is in one galaxy, another is in another galaxy. They will independently and randomly. When I'm saying independently means they do not have any prior information and they are not going to call each other and say, hey, I'm doing this measurement. Okay. So they're doing it independently and randomly. They select one of the three bases. When I'm saying randomly, I am assuming that it should be a truly random number. So again, it's a very interesting topic to discuss what is truly random and how can you measure whether something is random enough or not. But let me just say, as of now, we have some test suits and they should qualify them. Um, uh, then that is okay for me to use. But though I will prefer something which is theoretically more promising, perhaps a quantum random number generator. And I'll use it to select one of the three bases and measure the incoming photons in the polarization. So not much of a deviation, still same, only the thing is there I used two basis states and here I'm using three basis states, 0, 45 degree, 90 degree. Now, then comes the post-processing. The post-processing, we start off with the sifting. So in sifting, there's a basis disclosure. After all photons have been measured, measured means Alice and Bob are measuring, right? So Alice and Bob will communicate over a public but authenticated classical channel. Because I had already mentioned that I'm not solving this problem through QKD, but when I'm making a product, it has to be an authenticated classical channel. Alice should be talking to Bob. He should not be talking to Charlie. Okay, so it's an authenticated classical channel. And to compare which basis. They do not reveal the measurement outcomes. Very important. They never reveal because that is the key. So they do not reveal the key or they do not reveal the measurement outcomes. Though both are same. They discard any pair of where their chosen measurement settings were incompatible. Just like BBM92, where they were dropping some compatible or non-intended for key generation. For example, one is rectilinear basis, another is diagonal basis. So we will be dropping those test cases. Here is the difference. Here, they discard any pair of results which were chosen when their chosen measurement results were compatible or not intended for key generation. Not intended for key generation is very important, because here I am differentiate here lies a difference, because I'm using one set for testing the security, which means I'm using one set for doing the doing calculating the S factor, S parameter, if it is more than 2 or not, if it is still entangled or not, if it is still non-local or not. Okay, so here I'm using one set for testing the security, and if I know that it is greater than S, it is greater than 2, it is violating the Bell's inequality, then it is authenticated. I mean, it's a sure shot proof. It's a proof of a highest level. Okay. So for instance, if both happen to choose the basis corresponding to 45, 45, 90, 90, I will keep it for the key. In other cases, I may want to check the Bell inequality, which I'm testing the security of the channel. Okay. So the key generation from correlated foot outcomes, Bob and Alice used compatible bases generated for key generation, same as BBM92. Roughly 1/9 of the entangled pairs result in key bits if three bases are used. That means only 9n/2 end up in the key bits. And it is not very lucrative from the market perspective or practical perspective, because the throughput is very lesser. So BBM performs better than that. Okay, BBM 92, and hence that is also one of the reasons, if I'm doing it on a drone, then obviously I'll be losing a lot of photons because of the implementation and the propagation medium. Okay, so I have chosen BBM 92 because of certain practical aspects. But if security would have been my criteria, foremost priority, my priority, or a criteria for any application scenario, and definitely Eckert 91 would have been the choice. Even for education purpose, I think Eckert 91 is excellent, because it gives you the opportunity to understand to do S parameter evaluation, and to build trust in the source while doing the QKD. Security verification is Bell test. Okay, so, and yeah, I think that is all. And yes, finally, so here gone into more details, because from implementation perspective it is same as that of a BMF 92. It is only these differences where the S parameter, which we have already discussed earlier, is inclusive in that, and that is again coming out from the extracted bits, that how we derive the S parameter. I'll be using those measurement outcomes to fetch that value, and to if it satisfies the security criteria, then go ahead in building the keys. And interestingly also, this kind of a this kind of an approach is used for different other quantum communication protocols. See, because this is just one aspect which we are discussing today, quantum key distribution, but a secure communication through quantum communication can be achieved without actually distributing the keys, without the requirement of keys. It's called direct quantum communication, using conjugate coding and using the testing the security of the channel. So there are it opens up a very fascinating world of secure communication. There is another type of QKD called counterfactual QKD. Okay, so you are actually generating secure information without the medium actually going to the from Alice to Bob. So there are actually so many things to it. I'm sure I have just given some examples here, some standard examples, but lot is happening. And I will again suggest that you explore the different other methods of quantum communication apart from Eckert 91 or BBM 92 or standard prepare and measure kind of protocols. So in the end, I would again like to thank my team members, and we are doing all these interesting works in CDAC Pune, and our lab was established in March 2024. And since then, I think it's 1.5 years, we have been doing all the technology demonstrations. We have been building this up, and I could achieve this speed primarily because of my team and also because of the right selection of components and bringing right things together on table, and because of the mighty funded projects you know we have got to build on aerial quantum communication and terrestrial quantum key distribution. So now I'm again open for questions. Yes, so you can hear me, right?
Yes, ma'am.
Yeah, okay, great. Thank you. So, sir, any question you would want me to take?
So there are few questions posted by participants. So I can uh, I can read out to I can read out to you.
Okay, sir.
The first question is: does the collapse at the other end require propagation delay, or is it truly at once? How can we know?
Sir, which one? What is
It's
it? Collab.
it's posted at 3:16. Does the collapse at the other end require propagation delay, or is it truly at once? How can we know? Posted by
Please.
Agile. 3:16. Yes, this
Does the
one.
collapse? Oh, the collapse. Okay. Does the collapse at the other end require propagation delay, or is it truly at once? How do we know? So when I'm observing the timestamps of a coincidence event, that is actually giving me an indication whether it is happening at once or not. See, it is important. It is very difficult for me to say, because when I'm observing the timestamp, it comes with certain delays in the electronics in the implementation. So I have to trust the physics and the maths, because the wave function collapse comes from the mathematics, the linear algebra, the matrices which we are doing, and so every observable can be mapped onto an operator, right? And when we are doing the matrix multiplication, we are seeing it getting collapsed to these states, and when I'm doing it physically, I'm getting uh, the right answers the right way, whatever I'm seeing in the maths. But definitely it's not showing me the exact time, because I'm limited by those electronic delays of TDC, of synchronizer. But within a window of say 10 nanosecond, it is happening. So within a window of 10 nanosecond, if it happens, then I'm saying that it is a coincident event.
Okay, so the next question is during experiment, how the intersection looks different when the ambient light was turned on? Was
Oh
the
my God, no.
intersection staged?
Yeah, when ambient light is turned on, I mean, I switch off my detectors. The quantum experiment is halted. It's switched off before I switch on the ambient light, right? Because when I'm switching on the ambient light, then there is millions of photons coming to a detector, and the detector works in Geiger mode, and it will get burned. So I need to switch off my entire system before I turn on the light. The intersection becomes I disturb the intersection or the phase matching condition when I'm changing the phase matching condition. So I'm changing the orientation of uh, the direction of laser, or direction of propagation, or I'm changing the crystal orientation. The optic axis of the crystal gets changed by my changing the orientation. So I'm disturbing the phase matching condition in that manner, and then again bringing it back.
Okay, so the next question is there any plan to sell the complete quantum lab setup equipments for institution and universities?
There is absolutely plan, and the plan comes because I had suffered when I was doing these experiments in Bose Institute. It took a lot of time to for one event to happen, one phenomena to happen, and I exactly knew what I was lacking. So when this opportunity came, I brought everything together, and so when some strategic agencies also talks to me about building a lab for them, the whole lab is a different game altogether, and then you have to maintain that lab. So if I'm putting everything in a box, that kind of helps you to just set up the box in your room taking care of humidity and temperature. So if there is a center of excellence, you can do different experiments. You will know, the student will know about the they will practically know about the measurement postulates, the postulates of quantum mechanics, the state postulate. They will know about the unitary transformations, because if I'm doing a single photon experiments, whether it be QRNG, whether it be QKD, whether it be quantum computing, and I'm bringing all these three in a platform. So it's a very good I think EQ platform for quantum education. And I'll try to indigenize the the platform as much as possible and as possible. Why the
Okay.
wavelength has changed from 405 to 810? It's a non-linear process. So in non-linear process, it's a down conversion, parametric down conversion. Down conversion means my frequency is half, therefore my wavelength is doubled, and therefore 405 becomes 810, 810. Choice of wavelengths, it I do wavelength selection based on the performance of the system. So I have to take care of different equipments and their performance levels to decide on the wavelength. Saying okay, I'm confused that as we are saying that the Alice is sending some information to Bob in the information the- theory, but in the laser demonstration, you have shown that Alice is receiving a key and Bob is also receiving a key. Yes. So here my information gets generated on the from the quantum entangled source. So when I'm saying horizontal, vertical, these are the I'm assigning a horizontal state to a binary state, vertical state, state. So here in the entanglement based QKD, I'm receiving the states from a third party, and then I'm doing a QKD. That's how this thing is different than a prepare and measure, where Alice is preparing and Bob is receiving the key. So these two are different in terms of state generation and data transfer, how it is happening. Otherwise, what is the data remains the same for either one of them. These are these different types. See, because see, entanglement is a two particle state, and prepare and measure is a single particle state, and that's why we also differentiate categorize them into entanglement based QKD and a prepare and measure QKD. Prepare and measure QKD will not have a two particle state, na? So based on that, these they have been categorized. Alice and Bob share their measurement settings after the measurement. Do you know to know they are compatible or not? Would sharing those settings result in any insecurity? um no, they it should not, because and to ensure that I have to do it in a random manner. But if I'm using a random number of a lesser entropy of a biased random number, then of course it will give rise to any security. But at the moment, if I'm assuming that it is random enough, it should not. I don't see a reason why it should contribute to challenging the security. Can you explain anything related to four more discussed with entanglement? For modulations. I didn't get this question, I think. Can you explain anything related to four uh, MOD stands for modulation or discussed with entanglement? Horizontal, vertical motion of photons. I'm not sure I understand the question. I'm sorry. Okay, thank you. Yeah.
All right. So there is one more question. Probably we can take the last one and then conclude.
Talked about violation of Bell's inequality for QKD. So as I said that so if I'm not violating, so when Einstein was, yeah, I'll be sharing the presentation. So when Einstein was curious, he said spooky action at a distance, because that time the notion of non-locality was not there. Everything in Newtonian physics or in classical world was based on locality, localism or realism. Okay, so then they said that there must be some hidden variables, some pre-assigned value which we are not able to find out, or so maybe if there is something like that, then it should follow. It should adhere to the inequality which he has proposed. We should not be able to violate it. It should fall within that equality framework. But when we used a quantum entangled state, it actually violated the inequality, which shows that non-local measurement is genuine. It really happens. It is actually something that a state can become, uh, a ball can change its color, or the state changes its color upon measurement, is a reality, even if they are not locally connected. So from that perspective, it was a proof that this happens, which was then performed, or verified experimentally in 1980 or 1981, through some experiments. It's called CHSH inequality. So we have done actually that test, and we have shown that the inequality is it goes till 1.69, which is very high, which is still less than 2 root 2, which is very difficult to achieve. I would not say nobody has done it, but I think we are in a very good stage when we are saying that we have violated it with 2.69 factor. Yeah, I'll be
Okay.
sharing the presentation. Yes. Okay.
All right. So, a big thanks to you, ma'am, for your valuable time and accepting as a speaker in this program. And I hope the participants have enjoyed your knowledge on quantum key distribution in all these 4 sessions, and they have enjoyed the demonstration which you have shown related to the equipments which are required for the quantum key distribution. Now I request Professor Pillai to conclude the session.
Yeah, there's nothing much to add except to thank ma'am once again, and it's been a great partnership. And thank you so much, ma'am, for sharing your valuable experiences and all the effort that you put in developing the labs. And I hope that this will go into the participants' institutions as well. So we hope that the participants will take it seriously.
Thank you.
And they will try to approach you, and then hopefully we'll try to look at that. And ma'am has also helped us as MNIT in the lab proposal. So we will hope that we'll get through. And we will also have similar kind of mechanism. And Director has also granted given us an assurance that we will try to go further steps apart from the UG lab itself. So hopefully, as yesterday the MTech syllabus was also announced, and MTech programs can also be started. So some of these experiments will become the bare minimum that will be needed, where students will do their research work, students will do their dissertations and thesis. So this was one session which I advertised. I would say I put in a lot of effort to inform many of my friends. They have joined on YouTube because they were not registered with the course. So they have been, I said that this is something which ma'am has promised that she will do the demonstration and show. So I think this was something which was not possible in an online this thing, but ma'am has made it possible to put in all those things and do the video recordings and get the outputs and discuss everything. So it gives a confidence that right in India, we are able to do something like this. And right in our institutions, we're able to do this. So, most of you may not be knowing, but Dr. Anilita Banerjee was a teacher. She has taught in engineering colleges, and then she's done her PhD. So later, she's joined CDAC recently, you would say, I think 2-3 years ago. So I think that's a great career move and career change. So she's an inspiration for all of us here. And then I think the clarity with which she has communicated in 4 hours, so much content was given. I thank ma'am so much, and also CDAC and all the team members who are there. Many people would have worked behind the presentation to put everything in place. And hopefully, in the days to come, many of you who are teachers, many of you who are PhD holders, I hope that you will take these sessions seriously, and we will come up with many more such setups and experiments and also achievements. I think we will thank ma'am once again, and we also
Thank you, sir.
look forward for more sessions, especially that are practical in nature and as we continue these series of lectures. And today, as ma'am concludes her talk, it was 4 valuable hours. And thank you all participants, because you adjusted your timings yesterday. Half an hour it was before schedule because of a meeting that ma'am had. And thank all the participants who are patiently listening. And I was looking at the way that we are going through the questions, and you are following, you are asking, and some of you, I think, are digesting, because between the 2 sessions when ma'am was asking, nobody was asking. I wanted to join and inform. I was also a participant at that time. So I was not on the panel at that time. So I wanted to say that it takes time for these things to digest. So I hope the participants will go through the videos again as they are shared in the canvas. Please go through the videos. Please repeat these sessions so that you will understand more clearly. I wish you all the best, and thank you so much. Thank you, ma'am, once again. Yeah.
Thank you, sir.
We'll share the slides. Ma'am will share the slides. Yesterday's slides are already there. So today also we will put the slides there for you, right? Thank you so much, participants. We'll meet on Monday at 2 o'clock.